Welcome back to a new exercise. We begin now the study of objects in free fall. These kind of exercises are very similar to the ones that we have done already, but the main difference appears on the axis. Instead of things moving to the right or to the left, they're moving up and down. So our axis will not be the x-axis, but instead the y-axis. Thinking already ahead on the next chapter, in which we're going to have motion in 2 dimensions, I will be very careful on keeping all the appropriate labels. So all the tricks that we learned here in the y-axis, combined with what we learned already for the x-axis, can be used directly on the exercises for the next chapter. I decided to start with a very simple exercise so you can see how this works, how to set up the equations, how to draw the cartoon and choose the corresponding coordinates, and from there how to write the equation so you can get the exercise solved. Let's dive right in. A person throws a ball with a speed of 20 meters per second straight upwards. Find the maximum height that the ball will reach. Very simple exercise. There's only one piece of information, which is the velocity of the ball. Here there is no mention about the height of the person, so we can ignore that for now. Let's imagine this is maybe not a person, but maybe a cannon that is shooting this ball with this particular speed. It is important that it's being shot straight upwards. So the motion is again in one dimension, but it's moving up, and then it will of course move down. We are being asked to find the maximum altitude that this ball will reach. As before, we start with the cartoon. Our axis now is the y-axis instead of the x-axis. We usually call y-axis to this vertical direction. So the y-axis points up, and there is a person who will shoot from somewhere. So we usually put 0 here at the bottom, so this point represents y equals 0. The ball will start moving with some velocity vy0. Notice that I put the extra y here because this represents this velocity along the y-axis. For now this might be redundant, but it's going to be extremely useful if we keep using it because we're going to need it in the next chapter. Vy0 represents the initial velocity in the y-axis. This ball will move up, but at some point due to the action of gravity the ball will stop and will fall back down all the way to the ground. The question is where this happens. This point. We can call this h max. H in physics is usually used for denoting altitude, or the maximum height. This is why we use an h. And I'm going to call this h max because this represents the maximum height that the ball will reach. And it's going to be given in terms of the quantities that we have. So this is the situation. How do we solve this? For the exercises with acceleration along the x-axis, we were using the expression x, position being the initial position, plus the initial velocity times t, plus 1/2 of the acceleration times the square of the time. This is what we were doing in the previous exercises for the acceleration in the x direction. Now we use a very similar expression. We simply call y to be y0, meaning the initial coordinate in the y direction, the initial velocity in the y direction times t, plus 1/2 of the acceleration times the time. And here there is the other extra piece. We're never told about any acceleration at all. However, there is an acceleration. This acceleration is the acceleration of gravity. So the acceleration will be the acceleration of gravity. This is due to gravity. This is related to the weight of objects, so we're going to study that carefully in future chapters. But what really matters is that the value of this acceleration, or the magnitude of this acceleration, is 9.8 meters per second square. Now you're going to see something here a minus, and I want to clarify that right away. We call this acceleration g. In these exercises I will call g 9.8 meters per second square without any minus. The minus will be here in the front. In other words, I will write this equation as y equal y0 plus vy0 times t minus 1/2 gt square. This minus here is telling us that gravity always points down. Okay? This is the meaning of this minus. The minus in front of the factor 1/2 is telling us that gravity points down, and we're using our axis so that the y-axis points upwards. Since this is pointing in the opposite direction, there is a minus. But I don't want you to get confused about the idea of putting an extra minus in the value of g. The magnitude of g is 9.8 meters per second square. That's it. G, that's the magnitude, that is the number. The minus here, that only appears once, is telling us about the direction of that vector. Remember that acceleration is a vector, has a direction, can be represented by an arrow that points in the opposite direction of the y-axis. This is why there is a minus. So this is the formula that we are going to use for the position along the y-axis for free falling objects. Similarly, the other formulas that we have remain valid here. So we also have the expression for the velocity in the y-axis. We can put a little y if we want here. Will be the initial velocity plus the acceleration times time. In other words, Vy is Vy0 minus g times t. So this is our second formula that we can use. The only thing that I have done is I replace a by minus g. The third expression that we had before was for this formula without time. In that case, we had v final square is equal to v initial square plus 2 times acceleration times distance, x. In our case, this becomes Vy square is Vy initial square minus 2gy. So here is our third expression. So you can see these are not new formulas. These are the same formulas we had before, but we are changing a few labels, and we are explicitly telling the formulas that the acceleration is equal to minus 9.8 meters per second square. Okay, so let's now solve this exercise. As I mentioned a few times before, it is very important to know how to identify which formula is useful. In this particular case, there is no mention of time. So you should by now know what this means. It means that this formula here, the one that does not involve time, is the one that you should use. So let's write this on this box. Vy square is Vy initial square minus 2gy. So this formula is valid at any point on the motion of this ball. Now we're interested on the maximum altitude, the maximum height. So at this point, this is what we call the max point. So at the max point, we know that the velocity of the ball is 0. That's the definition of the max point. We know that the ball has to stop. So at the max point, we know that Vy is 0. We also know that y will be equal to h max. This is just a name that we gave to that point. So let us use these quantities and impose this condition in our formula. So the final velocity is 0, which square is 0. We have the initial velocity in y square minus 2 times g times y, which now is called h max. We can now solve this equation for h max. Let's pass this term to the left. We get 2 times g h max equal to Vy0 square. And now we divide by 2g and we get that h max is Vy initial square divided by 2g. And there we have it. This is a general formula that we can in fact include in our list of formulas over here. So we have the 3 main formulas in the boxes. We can also include this one because this is very generic. This formula has nothing to do with this particular exercise. Now we're going to plug the numbers and it will become particular for the exercise, but this is a general formula that I advise you to keep with you. Alright, so v squared becomes 20 meters per second, everything square, divided by 2 times g, which is 2 times 9.8 meters per second square. We have 20 square divided by 2 times 9.8, which is 20.4. We can simply write 20 meters. 20 meters. And that is the maximum height. In the next exercises, we're going to use these formulas several times so we can get more used to them. So make sure that you don't miss those.